think it's recording. Yes, okay, cool. So yeah, welcome to discussion 7. I think this is the first discussion post midterm. How are people feeling post midterm? Thumbs up, meh. Okay. Yeah, so I guess this week I think the lab has been adjusted to be due Wednesday instead of Monday. So if you're a little bit behind on that, I wouldn't freak out just yet. Maybe on Wednesday, if you're not done, I would freak out a little bit just then. But there should be office hours then, and project 2B isn't due for like another 2-ish weeks, or I think 1.5 weeks. So I would definitely take a look at it, but you don't need to freak out about it just yet. Yeah, and also in case you haven't seen the new mask update mandate thing from the university and the city of Berkeley is it's highly recommended, but it's not required. I'll personally be wearing it, but if for whatever reason, like you didn't have lunch because this is right after lunch or whatever, I guess we can't technically eat in here, but no one knows. Yeah, so it's going to be a mask recommended section, but if you don't, that's also totally fine. You won't get kicked out. Yeah, so we're just going to get started. I guess on a scale of up, middle to down, how are we feeling about Datapath stuff? Great. Okay. Okay, we're going to get started on that. So we'll first start out with a little bit of just general review. Do we want to do any SDS review, or are we feeling it? No. Okay. Okay, cool. Yeah, we'll skip over that. I wasn't sure from last time, but we're going to just jump into what single cycle Datapath is, and then we'll kind of briefly review control logic kind of through that, and then we'll get into the worksheet. The worksheet this week is really, really short, but it does include some important concepts. I don't think we'll get to designing new instructions today because it's also not on the discussion worksheet, but this is something like so pretty common question, I'd say, in past semesters. So I'll walk through some general tips on how to solve that. Sound good? Okay. So yeah, getting started, let's skip over SDS. Okay. Something that I just really want to, okay. So something I just want to point out is that when we get to our data path, it looks something like this. So this looks a little bit different from what you might see in lecture, just in terms of like how it looks. And it's because I decided to go and clean it up because I wanted to be able to manipulate things myself. But fundamentally, like all of the pieces are still the same. So yeah, wouldn't kind of pay too much attention to that. But you can see that like there are some elements in here that look, I keep spoiling a bit. So some parts that look familiar. If you've started doing lab 5, you might notice that like, oh, the ALU might like look sort of like a mux. Like there are these things, components. We'll talk more about each of them later and what they do. But first and foremost, because this is the tail end of like the SDS review, where are our state elements? So yeah, we have one at the reg file. Huh? DMEM, yep, because memory definitely keeps state. Huh? Yeah, IMEM instruction memory also keeps state. We store the instructions. And then yeah, not PC select, that's a signal, but yes, the PC register is also one. So we have these two going on right here. These are the ones that keep kind of our register system. And so like that's very obviously a state element because registers themselves are. And so these are like on chip memory, so they're really, really fast. But the other two pieces of state memory we have are IMEM and DMEM, IMEM being instruction memory and then DMEM being data memory. So these two are kind of, they're usually on the chip, they're stored in 2 separate components. For the like sake of this class, we kind of just like start out imagining them as like one piece that kind of got split up into 2 chunks. But in reality, they're separate pieces of hardware. Something that you'll notice is the same across all of them is this triangle at the bottom, and it's the triangle that I mentioned last discussion and during the review, which basically indicates that it's a timed piece of hardware. So everything else you can see like branch comparator, immediate generator, ALU, etc. None of them have the triangle, and that's because they're not timed. Like they have a propagation delay just because it takes time for signals to go through them, but they don't store any kind of memory or they don't store any data. Yeah, are there any questions about that? Wait, sorry? Sorry, I cannot speak today. A state element is basically a piece of hardware that can like have persistent, can hold persistent values. Like say if you feed something in it doesn't change until the next clock cycle. Whereas like, for example, like an AND gate that we covered in SCS, like as soon as the value passes through after however many nanoseconds, it just like doesn't know that it was there now. But like memory, very obviously, like it has some kind of persistent memory because you need to store things there. And so that's kind of what the state element does. So they are all timed by the clock, which is fed in through this triangle piece and or the triangle area. And then so on the next rising clock edge for each clock cycle, that's when things change. So, yeah, basically. One thing to note is IMM, you notice that, like, so for DMM, for example, here we have data W, which stands for data, right? And then for reg file, we have like data D, like data comes in as an input, and same for PC, like we can write it. But for IMM, we notice that we don't actually have any sort of write signal. And so the only thing that passes in through here is the PC value, which indexes into IMM and says, okay, I'm going to pull out like the instruction at this particular PC value or PC register value. So this kind of input arrow is just used as an indexing kind of method. And the reason that IMM is like you don't have any explicit writes to it. Anyone have a guess why? Yeah, it's the code. So we don't want to be modifying our own code. So in reality, this is like a very, very simplistic form of the data path. But in reality, like there are like ways that you can alter IMM or the code. But for the sake of like simplicity, it's kind of like, okay, this is like just blocked out. We don't even care about this at this point, and we will never be able to write to that explicitly ever. So if we remember from call, like during the loader stage, that's when like the system decides how to load the code into memory. So it loads it into this kind of read-only area, and then it says, okay, we're just not going to touch it after that. In real life, we'll talk about in like many, many lectures, the operating system can like decide how what gets edited and how it gets edited. So in theory, you could, but we will not consider that. Yeah. Yeah, so that's a great question. So for x86, okay. Yes, the short answer is yes. And a big reason of that is because of the way that the instructions are decoded. So like the fundamental setup of the stages and like of like what happens is like you can like box it to kind of be like, yeah, it generally does this. Like you have to fetch the instruction, you have to decode things, you have to execute like arithmetic operations, you have to access memory, and then you have to write back to things. Like that general flow remains kind of the same. Like how it's implemented is going to be different, but the most notable part that'll be different is this box that looks very, very simple. It's the control logic part, and that's because in here is where you decode the instruction to figure out what signals to pass to the data path. And x86 takes care of that in a very, very different way. And the data path itself will be a lot more complex. So like I remember like many, many eras ago when we talked about RISC versus CISC, RISC is like, okay, so the hardware is going to be really nice and simple and clean, and we want to do as little like hardware changes as possible between different instructions. So on the like user side, it might be a little more convoluted. But CISC is like, okay, the hardware is going to be insanely complex, but the user side is going to be a lot more simple because we have access to a lot more instructions. So it won't look like this. It'll look like a big giant mess. That's why also we don't study data path for x86. But to answer your questions, stages and general concept remain the same. Mm-hmm. Mm-hmm. Yeah, that's a great question. We actually get to that in a few slides. So IMM is just where all the instruction memory is stored. So when we go through, we do some form of like, for example, like load word, quote unquote, because a word is 32 bits, which is what we're trying to get for our instructions. And then so we can see that it feeds itself. Okay, so the output then goes here, gets kind of split up to access the reg file, and then also gets fed entirely down here. And so that's why we have an entire instruction, so 0 through 31 down here. So that way we can split up the bits. So if you have questions about any of the stages, we'll talk about that in approximately probably a minute. But yeah, this is just generally to go through. Okay, so now going into actual single cycle data paths. So the standard data path that we just saw, it counts for all instructions in the base RISC-V32 instruction set. So this is how you'll typically see it being written. On the exam, it was like base RISC-V32 bit instruction. Very, very long. So this is how you will see it kind of abbreviated a little bit. So this includes everything that you'll see on the reference card, excluding the mul operation, because that's a multiplication extension. So the wiring in the upper diagram that we saw earlier accounts for the flow of data. So the direction that the arrows point is like it starts from the end without the arrow and then goes towards the arrow. So sometimes you'll see it going to other parts of the data path. Sometimes you'll see it pointing towards the control logic. So the control logic block at the bottom, it just looks like a really simple rectangle, but that's actually the hardest part. And so that's also why for project 3A is really, really short. And that's why it also has a very short deadline. It's mostly to get you familiar with how things are set up. And then the second part is where all the logic is done. It's like you break up the instructions, you figure out how to do each of these operations based off of the bits that you're fed. So the control logic, so right here we have CL, that stands for control logic, not combinatorial logic. But the control logic takes the data or whatever signal is passed from the data path. And in this case, the arrows point towards the control logic. So that includes things like, for example, the instruction 0 through 32 bits, includes the, I think it was branch unsigned, I believe. And I think one other thing that I'm forgetting right now because I'm not looking at it. Oh, yeah, okay. So I wrote it here, but instruction branch equals and then branch less than. So what this does is basically the data path itself tells the control logic what to do next. So this is really starkly different from all our other signals, which is from the control logic to the data path. So these particular ones going from data path to control logic tell the control logic, okay, I need you to compare something this way, or I need you to break something else down. And so that's what these three signals take care of. Does that make sense? Okay. And then the control logic that feeds signal back to the data path, they point away from the control logic. So this is basically everything else. So all the selector bits, all the write enables and things like that. So these signals are calculated during the control logic based off of the instruction or instruction signals that were sent, and then later on based off of the branch equal, branch less than signals. So really quickly to jump back to this point, the reason that these are fed from control logic, or sorry, from data path to control logic is because, well, first we need to know what instruction we're breaking down. So does that make sense why we needed to go from data path to control logic? Okay, so then for branch equals and branch less than, so this doesn't actually happen in the control logic. And the reason is because we don't need to look at the bits and then also include some really big piece of hardware in there to do that. Instead, we can kind of couple it all in with the execute stage. We'll see that later. And then based off of what happens there, then our control logic kind of signals will change because we might want to jump, we might not want to jump. And so that'll determine what execute does later on. So these are, yeah, so kind of jumping back to this, going from control logic to data path are all the other signals that we have. And the different stages that we have, well, these kind of correspond to what happens in each of the components. So we can separate these out to basically be, okay, these things kind of happen pretty much all at once. These happen all at once. But because we're in the single cycle data path, they can't all happen at the same time. So if we take a look at our data path right here, our first stage is instruction fetch, and it sort of ends approximately between IMEM and register file. And the reason for that is because, well, what happens here is our first stage kind of updates the value in the PC with the ALU output or the old PC +4. So we can see how this is kind of wired. We have a mux right here, or a multiplexer. And what that does is basically it says, okay, so I have 2 or more values that I want to pass out, and I want to choose between one of them. So we might have like, for example, here we have PC +4, which is the return or the value or the next instruction. And then sometimes we might want to jump. So we might want to have PC plus some other offset. And so PC cell or PC selector down here kind of takes that and says, okay, well, based on the signal that I pass here, I'll then output either what's going into the 1 kind of input or 0 input or the 1 input. And then that gets written to the PC at the next kind of clock cycle. So this updates the PC. And then so after the clock to Q time, when this output can be read, then we're going to look into IMEM and say, okay, well, whatever the PC has, it's going to be some valid instruction memory address. We're going to assume that. And then we're going to fetch that from instruction memory. And then it directs it to the data path. So here we can see it's broken down into various other components. It's broken down into 7 through 31 for the immediate generator. And then the entire instruction is fed into the control logic to be broken down into all these other signals over here. And then we also notice that the PC +4 kind of gets fed up here. So we have a PC value that kind of gets fed into the next kind of stages over here. We'll ignore that for now. But we also noticed that it goes through a +4 kind of adder block. So this is just a very standard kind of add 4. And we can see that this value kind of gets fed back into the PC cell multiplexer for the next stage or for the next instruction. And then it also gets kind of split and fed all the way over here to the output 2 right here, which we'll talk about at the very end. Yeah. Here? Yeah, so the 0 and 1 here, they're not the values. They are kind of the positions. Like you have hardware and then you sometimes like, how many people here have taken some sort of EE class? Okay, so I guess I will not. But so basically when you have kind of hardware or like just anything, you can have like different pins that you slot things into and like say, okay, maybe like, for example, our, what's it called? Our AND gate from the previous section, they usually take 2 inputs. And then so we have input 0, input 1. And so that's just where the kind of inputs get slotted. And inside the hardware, it figures out, okay, this is the input from 0, this is the input from 1. I'll do some magic and then output something else. So here it's saying, okay, our, let's see, 0 is mapped to. So 0 is mapped to old PC +4 because we can see that's where the kind of wires follow. And so PC +4 is going into here, and then PC plus whatever offset it is the output from the ALU way later on. And then PC select kind of either is going to be of 2 values. So it's either going to be 0 or 1. If PC select is 0, then the PC +4 value is going to be written into this register. If it's 1, then it's going to be PC plus whatever offset that we have, and that's going to be written to the register.
But it can only be one.
Yeah, it can only be one of the 2 values. And we can see later, like there's another mux over here, and it has 3 possible value outputs. So we'll talk about how that's done later. Yeah. Yeah, so if we kind of trace that back, so we have one output here, that's the PC +4 right here. And then the other one is kind of going, okay, we trace it all the way here, and then we keep going, and then we keep going, and it's tracing from this intersection, which is the output of the ALU. So it's coming from here, yeah. Yeah. Exactly, yeah. So something that it might be useful for that is when we have a jump instruction because, or jump or for example, branch instruction in particular, because we either want to go to the next instruction or some jump to a label later on. So if we want to go to the next instruction, the PC select would be set to 0 because it wants to be PC +4. If it does decide to jump, then it's going to be the output of the ALU. Mm-hmm. Mm-hmm. Yeah. Yeah, so it's just it's you can think of it as just like standard memory, and PC is just like some address that happens to address it. So theoretically it could be invalid as well. It's just we assume that it's some valid INN address. Yeah, the CL and then the rest of the data path as well. Mm-hmm. Yeah. Yeah, so if PC cell is selected as 1, then it's going to take the output from the ALU because so kind of in all of this, we assume that the wires kind of propagation delay is 0, which just means that any value that you see being passed along a wire is instantaneous. So basically you can assume that like, okay, this output just gets fed back into here instantly. So does that make sense? Like why 1 is the output of the ALU?
But then there's like there's a function, but then there's also like a factor of like whether the how do you know that the coming out of the from that mass?
Which mass?
This from the mass capacity.
Oh, you mean like this area?
No, the one
Here?
the one over here, like on top of the
On top of the
yeah, if you go, yeah, there's like so an ALU, there's like the one, yeah, but then there's also another one going like the same way as the input of letter.
Like over here.
Yes. So how would the normal input that's coming into the first is from the
Oh, okay. I get your question. Okay, so right here, we have a junction right here which splits into two directions. So what we can say here is just the value that's traveling along this wire gets copied into both of these wires, and then they respectively go to where they need to go. So here we can see like the arrow points this direction into the mux, so the value like wouldn't pass backwards. So a mux, like it takes in a value and then outputs something else. It doesn't like go the other way around, if that makes sense. Yeah, so it's a good question. Yeah, this one? That's the control logic. It's it's not kind of drawn out ever because it gets much too complicated. And also like you can implement it in a lot of different ways. Okay, and then so what happens after that is, so we access the instruction memory, we see that, and then the PC register, and then we access the PC selector mux, which is this one, and then the +4 adder. So those are the different components that get accessed during instruction fetch. Are there any questions? 0 and 1? Yeah, so here we have the PC. So what happens here is from the previous kind of clock edge, we have the value that gets selected from this PC selector mux, which takes either this input, which is the ALU output, or the 0, which is PC +4, and then we store it in the PC value on the next clock cycle. And then after the clock to Q kind of time, because that's when the output can be read from a register, we take that and then we address IMEM with that. No, PC is going to have an address. So 0 or 1 is just indicating the position of the mux that PC select is going to select.
So no matter what value the mux output,
it doesn't, the PC selector mux doesn't output 1 or 0. This is just the positions of the values that are going to be outputted. So say if we have value A and value B here, if PC cell is 0, then it's going to output A. If its PC cell is 1, then it's going to output B. Mm-hmm. If it's selected, sorry, what? Yeah. Yeah, so if PC select is 1, then the value of PC is going to eventually be that 1, which is from the output of ALU. Huh? No, that's only if it's 0. So the add 4 happens afterwards, after it gets kind of, this is basically prepping our next instruction. So the +4 here is happening at the same time that we're kind of accessing IMEM. And what it's basically doing is saying, okay, we're going to execute some instruction at position M. And so the next instruction in theory that we're supposed to execute after that is going to be M +4 because +4 bytes. Okay, I'm going to just go into the next slide. It might help a little to understand what the signal is doing. So after each of the steps, we're going to kind of have a comprehensive slide with the possible control signals for the different, or the possible signal values for the control signal. Also, if I like start talking not very loudly, it's because I am starting to have a really bad stomach ache of some sort. So let's see if like I can keep it up. But the control signals, so for here, we can see that we have PC select. And the two signals that could have are either 0 or 1. So for 0, it's going to fetch the subsequent instruction. Oopsies. Okay. Hold tight. Oh, okay. I think the Wi-Fi just kind of died for a moment. Okay, there we go. So yeah, if we have 0, then it's going to get the next instruction. So typically this is going to be a return address value, or it's going to be the default next PC value, because the next instruction that we're trying to execute. And then if it's 1, it's used for typically jumping or branching instructions because our next instruction typically isn't going to be the one that's next in memory. So this is usually when the PC will be plus offset will be greater than or equal to 4 bytes. So you can note here that the PC select will never be star, which is defined as don't care. So it means that whether it's 0 or 1, it's not going to affect the execution of this instruction. And this is never not care because we always want to know and we always want to control what our next signal will be. Like we will never not care if we jump or not. Like there's no randomness in this. So that's why the star will never happen. So to clarify, I think this was a confusion or point of confusion in lecture, but the star is not some other third or fourth signal. It's just going to be like we don't really care if the wire that's carrying the signal is 0 or 1. So it's going to be one of the two. We just won't control what it is. And so it's not an additional signal that we have. Does that make sense? Okay, and then the other control signal is instruction, the instruction itself. So the signal that this carries is kind of NA because it's not going from a control logic to data path. It's going from data path to control. And so this is the base instruction to be broken down into other signals later on. Does that make sense? Okay, so going to the next part. The next part is instruction decode, and it's typically abbreviated as ID or just D. And we can see that this encompasses a big fat chunk of the middle section, which includes the reg file, as well as the media generator, so imgen right here. So what happens here is we first parse the instruction that we get from instruction fetch into the more useful signals. So we can see that it gets passed over here. There are 25 bits that get passed to immediate generator, and this eventually spits out a full 32 bits worth of immediate to be used later on. And we can also see that it gets broken down into these 5-bit chunks. And these, can anyone guess what these are? Yeah, exactly. RS1, RS2, and then RG right here. So we can see that there are 5 bits. And what it might be a little confusing because it says adder, or which stands for address D, address A, and address B. What this actually means is basically a reg file is something that's to be indexed, same as memory. Memory is just bytes to be indexed. A reg file is just registers to be indexed. And so these are technically addresses for the reg file. So if we, for example, say, oh, we want X3, then our kind of address is going to be 3, and then we kind of index into the third position at the reg file, and then we get the output of that. And then we access the reg file, so we identify the useful registers that we need. We read from the source registers and then pass whatever data that they contain out. So we can see at data A, data B corresponds to the data that the registers at adder A and adder B kind of hold right there. The next stage is accessing the immediate generator. So this generates a full 32-bit immediate based on the instruction type. So we have 6 explicit instruction types, 7 if we include I star. And then we have 5 or 6 immediate types based off of that because our R-type instructions, like they don't have immediates that we need to use. And so that helps us decide whether or not we want to 0 or sign extend. And we also need to piece together bits correctly because we remember that some immediates have like bits broken down into say like 12th bit and then like 4 through 0 and then 11 and then like subsequently. So it gets messy a lot. So the immediate generator takes care of that. Yeah. Mm-hmm. Which multiplexers?
So
I think you are seeing it in an opposite direction. So the arrows point in the direction of the data. So it goes from data B, data A to the multiplexers. Wait, sorry, I don't feel very good right now. Give me 1 moment. I think I'll use the restroom or go to the restroom for a second, sorry. Okay. I think where we left off was, I think the last question was, oh, do these multiplexers not affect like what the data is? And the reason that it doesn't is because like, oh, the arrows point in the direction that the data is flowing. So it doesn't flow backwards. Like the multiplexers will not affect what data kind of gets outputted over here. The data outputted is only going in this direction. Does that make sense? Okay. Cool. So then the instruction decode section, we have these control signals. So in cell, we have I star specifically is referring to specific instruction types, which are, or instructions, which is like, for example, I think it was like shift left arithmetic immediate. For example, we have store instruction type, branch, upper immediate, and then jump. And the reason that we have each of these is because they process immediates differently and they start with a different number of bits. So if we kind of go back to our previous slide right here, we can see that the immediate kind of that gets fed in here is basically all the bytes or all the bits other than the opcode. So it's literally everything that's not the lower 7 bits. And we can't just take that and be like, yeah, let's just extend that, because it includes our, for example, our register indices. It includes our func7, func3, for example. And so we need to be able to decode them first and then extend them after that. So that's why our signals for that are so important, because we need to know how to piece together the immediate. So these signals, like when you're actually building your data path, they're not going to be like I star S or whatever. You're going to be assigning specific values to each of them. And so these are going to be used in a way that's almost like a multiplexer as well, because you have one input, you're going to do a bunch of things to them based off of the instruction type, which is determined by the opcode. You're going to figure out basically how to extend and piece together those bits. And then you're going to output one value. And then we have the reg write enable, so reg wn. And so we can see that that's fed into the reg file right here. So this is not data that's going to be written. That's data D right here, data destination. Instead, what it's saying is basically it's telling us whether or not we're allowed to actually write to the reg file. AKA, are we allowed to write to whatever register that we're specifying based off of the address D right here? So we can specify a register, but if we don't want to write something, then no matter what the data is right here, or no matter if there's valid data, we're still not going to be able to write to it. So we have two signals that's available there, 0 versus 1. So 0, when reg write enable is set to 0, nothing can be written to the reg file, no matter how valid your data is. Whereas if it's set as 1, even if the data that's being written back is invalid, it'll still be able to write. So basically, this is acting as kind of the gate that's telling us, okay, we can't write anything. Okay, we can write whatever we want, basically. So this is a note, this will never be a star or don't care. Why is that? Huh? Yeah. Yeah, so one instruction can't do both read and write. We also specifically want to specify whether reading or writing. What, were you going to say something? Yeah, exactly. So so what you were saying was, you want to specifically write, or aka have a reg write enable only when we have a RD or destination register. Otherwise, even if we have values right there and it gets decoded like that, because like we notice in the instruction or the instruction breakdown right here, we don't specify whether or not like adder D or RD value is going to be valid or not. So it's going to decode this no matter what. And we're always going to have some sort of data D, regardless of what, because it's going to be passed back through the write back stage right here, which we'll talk about later. So these two values, the adder D and data D, are both going to be populated no matter what. So if we didn't have this enable versus disable signal, then we're always going to be able to write to whatever register is specified here. So it might overwrite valid or valid data that we don't want to overwrite. Does that make sense? Yeah. Immediate self? Yeah, that's a great question. So for this one, we don't care. If, for example, there's only one type of instruction really that we don't care on, that we like that we study at least in 61C, which is R type, right? Because that one doesn't have an immediate. So if it's an R type, and then we just decide, okay, let's generate some random immediate, and that's what let's follow the output of immediate generator. So output goes to here and here only. So here we can see that this is determined by some B cell right here, or B selector. So it's going to be the input B right here, selecting what goes in there. So this will only get selected if the instruction tells us that we want an immediate. So for example, if we have an R type instruction, we'll only ever select 0. So we don't care what input goes here. So kind of going along with that, let's go to the execute stage, which is this next section. So we can see that it does a bulk of our computation. So that does our ALU, so arithmetic arithmetic logic unit. So this is doing most of our computations. So add, subtract, shifts, all of those things. And then we have our branch comparator right here, which does the majority or all of our comparisons between our register values. So if it's a B type instruction, aka if the opcode tells us it's a B type, then we compare two values in the specified format from the control logic. So here's something that you might notice. Right here, we can see that our branch unsigned is going from control logic 2. So yeah, this is slightly offset just because of the spacing. I apparently forgot to fix it. But so we have branch less than right here, branch equal to here, and then so this is the branch unsigned. So branch unsigned is going from the control logic to the branch comparator, because this is telling the branch comparator for the two inputs that I get from here, which is coming from data A and data B, I want to compare them either in an unsigned format or a signed format. And this is really important because maybe not for branch equals, because branch equals either like the bits are the same or they're not the same, but for branch less than and thus branch greater or equal to, it really matters because, for example, if we have, say, like a bunch of ones and then some zeros, if we compare that in an unsigned versus signed format, it's going to give us different results. Because if we interpret it in a signed format, then a bunch of ones in the front followed by a bunch of zeros is going to give us a negative value. Whereas if it's compared in a signed format, it's going to give us a really large positive value. So our comparison for branch less than is going to be different based off of that. Does that make sense? Okay. So then it sends the signals to control logic to determine what next instructions happen. So after we do our comparison, then the control logic kind of gets fed this. And then so based off of this, we're going to basically decide, okay, what next values are we going to choose? So any other instruction, we're just going to do an ALU. And this is not just confined to, for example, add or sub or shifts. The reason is because, well, if we have JAL-R instructions, if we have branch instructions as well, if we have memory instructions, all of them will include some kind of addition or subtraction. And so if we kind of go through each of those. So if we have JAL or JAL-R instructions, if we have JAL or JAL-R instructions, how does arithmetic operations play into that? Yeah, exactly. So our base address register, base register plus the offset that we're giving for JAL-R, or our PC plus the offset for JAL instructions. Same for branch instruction. It's another PC relative address kind of indexing. So we have PC plus offset. And then for our memory accesses, so load word, store word, etc., all of those, we also have a base address plus the offset. So ALU will get, and I think this is true, but it'll get used for effectively every instruction that you will ever try to decode in this class. So this is a really important unit. Does that make sense? Why? Okay. So these are used for standard, updating PC, calculating offsets, etc. Something that you'll notice is the ALU input has two. So we have A right here and then B right here. So A cell, it determines what input goes into the A input for ALU. So we can see that one of the inputs is 0 and one of the inputs is 1. And same for the B cell right here. So we can see it being mapped to right here. B cell also selects 0 or 1. And on the next slide, we'll see what each of those does. But if we follow the arrows, we can see that data B kind of goes into 0, whereas immediate goes into 1 for B. And then for the AMUX, then we can see that for 1, the PC value goes into 1. And then for 0, the data A goes into 0. So this is a really large chart. You don't have to memorize it. You can use this as a reference. But so A cell and B cell, we can both use don't care. And the reason for that is because sometimes, like for example, if we, for example, happen to not want to use the ALU, then you can theoretically use don't care, because I can't make the broad claim that no instruction ever doesn't use that. So in the rare instances that that does happen, you can use don't care. But typically for instructions that you want to decode, you almost always want to specify a 0 or 1, because the ALU output is something that you care about. So ALU cell theoretically then in that case shouldn't practically use this. I think should be copied to both here, but in theory you can use don't care, but in reality you probably shouldn't, because it just determines the output of so many operations that you probably want to specify something. And so for ALU, it selects the basic arithmetic operation that the ALU performs, and it's used in almost every instruction. So in project 3, you'll notice that there's going to be a chart basically of like, okay, you want to implement this instruction A, B, C, D, like all the different operations. And so the ALU winds up being, again, one giant mux that you use kind of a selector to decide what value or what operation you're going to execute. And then for A and B, this selects the input to A or B for the ALU, and then 0 is the standard register value from data A. 0 for B cell is the standard register value from data B. And then for A, the one selector is the PC. So this is used for things, so not JAL-R, sorry, it's supposed to be for JAL. I'll fix that afterwards, but this is supposed to be for JAL, for branch, etc. And then for the BMUX, it's going to be an immediate. And then so we get our giant branching kind of line. We can use star for all the instructions except for branch instructions. And that's just because, well, our branch comparator isn't going to be used for any other instructions. So we have our branch unsigned. So this goes from control to data path. So it decides how the branch comparator works. And then for the other two, it goes from data path to control. And this determines what our next instruction is going to be. Are there any questions? Okay. Huh? Oh, yeah, I do feel better. I don't know what it might be something I ate for lunch because I threw up in the bathroom, but now I feel a lot better. And also I think that Advil probably helps. So we're good. At least for now. We'll see. Maybe I have food poisoning. We'll see. Update for next Monday. Caroline had food poisoning. No, I'm good. Yeah, thanks for asking though. Okay, so moving on to the next part. By the way, so we're going to go through a lot of practice for this, and a lot of past exams have like, oh, like for this instruction, what are all the signals that kind of get put in? And so it would help if you're like kind of familiar with each of these, but if you can read a data path and see like, okay, so this goes from here to here, then in theory, you wouldn't need to like have a chart of like, okay, this exact signal is for this other thing, because the data path should make it kind of obvious, but like as a Hail Mary, if you want to include it on your cheat sheet or something, it's totally okay to do that because no one expects you to memorize the data path. Yeah, for our second to last stage, we have our memory access or our mem or M stage. And this is exclusive to just doing the DMEM part. And so what this happens is, oh, apparently I forgot to add the animations for this, but so for DMEM, we write if enabled, otherwise we're always going to read. So what does write enabled mean? Well, we have our mem read right here. And so this is the signal that basically acts the same way as like reg write enable. And so this being set to 1 means that we're going to write to DMEM or data memory. Otherwise, we're always going to read from it. So the question here is then like, okay, well, there are many questions here, but the other question is kind of, well, why do we like not just bypass a data memory? Because we know that accessing memory or main memory is going to be pretty slow. So why do we access it regardless of what our instruction is? For example, like most of our instructions aren't ever going to need the data read from DMEM. So why do we do it? Simplicity, yeah. So simplicity is a big part of it. So part of the other thing is there are two kind of subpart answers to that. So the first one is that like access to main memory is kind of like not clocked in the exact same way that you would clock the data path. So it's done almost asynchronously because it can fetch something kind of quote unquote, not really on the fly, but kind of like off of the timing of our actual data path. But we consider that to be in the executing time for the memory stage itself. So we'll see that on the worksheet in a second. The other reason is because our data path, especially for single cycle data path, is timed to literally our longest instruction. So our longest instruction, spoiler alert, is going to be load word, because well, we have to go through instruction fetch, instruction decode, and execute for all stages. For load word in particular, we have to write to memory, which is going to take longer than reading. And then we also have to load that whatever is being, we have to access memory as a read. And then whatever we're reading has to be written back to the reg file because we're loading from memory. So it's going to hit all 5 stages actively. And so in that kind of, by that model, our other instructions should be timed in the same way. Like it can't go faster, otherwise we're going to mess up timing. Yeah. Mm-hmm. Yeah, that's a great question. So the question was for online, basically, how do you tell how long it takes to read something? And yeah, like the time that it takes varies based off of like what you're trying to fetch, as a spoiler alert for in later sections, whether you have a cache or not, et cetera, et cetera. The details are kind of complicated, but basically like you just get kind of like the word is not homogenized. I'm forgetting what the term is, but basically, yeah, it's kind of getting like the general average of a bunch of different accesses to like that particular address. And then that's the general time that it takes. In problems, you'll always be given like, oh, data memory kind of takes like 200 milliseconds to access or something like that. So you don't ever have to calculate it, which is a relief. But yeah, so the time here is like, it's not like particularly accurate, usually like in the sense that like, oh, if you try to time a particular access, it'll be exactly that. It's just like generally this is what it is. Yeah. Okay, so I'm going to skip over bullet point 1. This is under the assumption that we've covered all of pipelining already, which we have not yet. But the last question is like, okay, memory write, read write. Why should it never be star or don't care? Yeah, so same reason as why read write enable isn't ever star. And the reason is just because we don't want to mess up memory. We don't want to be writing to memory in an instance that we're not trying to actively write to it. For example, if we don't have a store instruction, we don't want some other random instruction just feeding things in and being like, yeah, let's write to here. Because if we look at the inputs here, as a reminder, like hardware isn't really ever like, if this is something, then we're going to do that. Like it cannot think. So the values being passed along the wires will never just be like non-existent. It'll either be 0 or just some other random value. And so we consider that to be garbage values. So if we kind of take a look at that, data W or data being written is kind of goes all the way back to it's being read from data B right here. And this output is always going to be something no matter what, because we don't specify whether or not like, oh, in this particular instruction type, we're going to read this at this position. Instead, it always decodes that no matter what. And so we're going to sometimes, like, for example, if we have a, let's say, add-I instruction, it's going to have some register that you're reading from. So we're going to pass this data into data B. It's going to be passed along this wire all the way to data W, and it stops here. And then it says, okay, well, add-I instructions, obviously it's going to go through the ALU, and it's going to add some 2 values together. And so whatever this is adding, it's going to be passed into the address right here. And so if the mem read write is a don't care, and the don't care happens to be a 1, then what it does is says, okay, this random address that I calculated as the output of some add-I instruction, that's probably not a valid address. We're going to try to access that, write whatever data it is here that we wanted, and then we're going to read something else as well. And so this is basically, it just has no sense of whether or not you should be doing something. So that's what the mem read write is taking care of. It controls that. That makes sense? Okay. And then here we also eventually calculate PC plus 4 for the write back mux. So right here, we can see that this data gets passed along all the way over here, all the way to the write back mux. Sometime so on the worksheet, I believe you'll see that there's a PC plus 4 block somewhere in this vicinity as well. So let me make sure. Where is it? Oh, I think we might have removed it at some point. But at some point, basically, there was a PC+4 mux that was right here, as opposed to kind of passing this entire value all the way down. So why might we want to, for example, include the PC+4 right here instead of over here? Because we know that PC+4 needs to be fed into, I think it is PC+4, let's trace this. It needs to be fed into input 2, so we could theoretically calculate it right before this mux, or we could calculate it during this stage, the memory stage. I would say, like, in theory, no, if you were just designing your very like independent data path, because you can just choose, okay, what goes into what. But we want to have a general standard because, like, say, if like an instruction, because it depends on your control logic. So if we want a standard, the standard is, okay, the write back is 0 for memory, 1 for ALU, 2 for PC+4. So yeah, just to answer this question, the reason that we would, if we didn't pass the +4 all the way from instruction fetch, and instead we, like, for example, pass just the PC value all the way over here. Instead, we would want to calculate PC+4 here instead of during the write back stage, because it can happen in parallel with DMEM access as opposed to serially before the write back mux. So doing it here would take extra time. Doing it in mem stage would not cause extra time because it could happen at the same time as the much longer data read or memory read. Yeah, great question. So let's kind of mess with this a little bit. So let's say we had, okay, we're gonna just include this +4. Nope, that's not it. Yeah, there we go. So if we instead like put the +4 here, so assuming that, like, for example, we had, so we see that our PC value goes from here, and then say, instead of this, like, let's say this only went to here, and then we have, like, say, yeah, this is how I edited the data path. So instead for here, we have something along the lines of this. Okay. So do we see how here we changed the data path? So instead of having a +4, which just feeds back here, we instead pass the PC value all the way over here. Does that make sense? Okay. So instead we want to have, oh, I guess I didn't copy the whole thing. I don't know if I can. I'm just going to do the +4 and hope that it suffices. So if we have the +4 right here, so on this line, so this happens, this +4 adder happens at the same time that DMEM gets access. And we know just by default that accessing main memory is going to take a lot longer than an arithmetic operation. So by an order of probably like 10 to 100. And so doing it here, it happens at the same time. So we just take the max of the two to figure out how much time that kind of stage takes. So the max would take, okay, DMEM, no matter what. Does that make sense so far? Why? Okay, so instead, if we decided to say, like, let's do +4 right before this. So imagine there's a +4 right there. So it happens right before our mux right here, and it happens in the write back stage. What happens here instead is, because it's executed after DMEM finishes, then we have to first calculate PC+4 before we can go to the write back mux and say, okay, now we can properly select the value. So this is the difference between doing things serially versus doing things in parallel. So in parallel, it's going to take the max of all the operations, whereas in serial, it's going to add them no matter what. So we would have the extra time that it takes to do +4 during this stage. Does that make sense? Okay, so. Exactly. Now I'm kind of like, want to make sure this is lined up. Nope, it's not lined up. It's fine. Everything's fine. Oh well, I'll edit this later. But so that's the reason that we also passed the PC+4 from over there. So I just kept this diagram just for to show the difference. But in theory, there are different ways that you could wire this up. So we just want to make sure that we have the lowest overall amount of time. So we try to do things in parallel when possible. So that's why, for example, branch comparator happens during ALU, because in theory, it could happen during its own branch stage, But because these two, ALU and then branch comparator, don't have any dependencies on each other, we're able to put it in the same stage and still be okay.
Class 4
If you move, if you took a copy of this +4 and stuck it here like we did before, yeah, so it would be the same amount of time because max of the PC +4 versus the DMM access is going to win every time. So yeah. Exactly. Yeah. So immediate generator, it doesn't depend on what's outputted from the reg file. Same with the kind of like, for example, we can see all of these, the PC mux and then the PC register and IMEM, they're all in serial, but the +4 and the IMEM are in parallel. And the reason for that is because, well, PC register's value depends on whatever is outputted from here. IMEM's access depends on the PC, but after we get that, this access for PC and then the PC +4 don't depend on each other. That makes sense? Okay, so when we're calculating things later, like how long like data path cycles should be, when you're like looking at something, then you could take, okay, so if things happen in parallel, then we can take the max of the values and not incorporate all of them. Whereas if things are in serial, then we have to add all of the components times. Okay, let's move on to the next part. So the exit. Oh, this should say mem control signals, but the one signal that we really care about is mem read write. This should never use star. 0 is do not write to memory. Basically, it's a compulsive read, and 1 is a write data write to at position address. So this one is used specifically for store. So we can say store byte unsigned, store half unsigned, store word, etc. And then 0 is any other operation that isn't store, basically. So we can see over here that the output happens no matter what. So it's going to read an address no matter what happens, because again, our data path is not like selective. So it's going to output here no matter what. But based off of our write back selector, which we'll talk about in the next stage, the output here doesn't necessarily always get written to or written by the memory read. Okay, so then for our last stage, we can see that we have write back select, and it kind of happens in the very end as well as the very beginning right here. And that's just because everything kind of wraps around. There's no explicit start or end here. So what happens during the write back portion is it selects the value to mux out. So it's either going to be the return address PC +4 at position 2, ALU, which is pretty standard, which is at position 1, and then memory, which is loading from memory at position 0. So this is a star, so any value can be returned. So this is our kind of quote unquote third signal. And so the reason that we sometimes don't care about this is because sometimes our instruction operation doesn't actually have a a destination register. So in that kind of case, our register write enable won't actually have 1 being set. So it's going to be 0. And so no matter what we output here, it won't matter. Does that make sense? Yeah, so jumps in, well, okay, jumps, so JAL, sometimes you'll have a return address, right? So sometimes that'll be written to, and we'll have our write back selector as 2. But for branches, yeah, we won't have a written. And for example, for stores, we also don't have a write back. So the interesting thing for stores is that we have one address that we're both reading and writing from. So what will happen is the data write kind of portion will say, okay, we're explicitly writing to data, but the data read here is going to be some random garbage output. It might be what we just wrote. It might be the previous value at like our position, or it might be some previous read that we like from the previous instruction. So stores kind of have a weird output here where it's like, we don't really care what's outputted, but it's really interesting because there are like 3 different possibilities. Okay, so we just talked about this. So, yes. So I keep forgetting to change the titles of the slides, but this is for the write back selector. So we can see that the one signal that we have is write back cell. And so 0 sends memory data to the register. 1 sends the ALU output to register. 2 sends the PC +4 register. And 3 we are going to have some random 3 signal. So question is, well, why do we have this 3 signal if it's not being used? So So think about our wires. So for our previous stages, so for PC cell, A cell, B cell, etc., we only have two values that are possible, 0 or 1. And so a one bit input will be able to take care of all of those. But for right back cell, we have at the very minimum like 3 different inputs that we want to have. So 1-bit inputs or selectors aren't going to be enough. So we'll have a 2-bit selector. The 2-bit selectors by default are able to be set to 4 values. So it's 0, 1, 2, or 3. So in theory, like you have this random third value that you could set it to be as. You could set this to be don't care. It's just going to exist just because of the nature of right back selector is a 2-bit selector. Does that make sense? Okay. Yeah, so 3 is like it just exists because it has to exist because 2-bit inputs require 4 values. Okay, so that's the end of the review that I have. Are there any general questions overall? Yeah, so I guess understanding the data path, honestly, the best way to do it is project 3, which is, I know. So understanding the data path, like the intricacies of how everything works and how everything is broken down, that's actually just the best way. That being said, on exams, you're not going to be tested on like reproduce this part of your control logic. So that's definitely not the case, but it really helps understand like why instruction formats are the way that they are and everything like related to that. For the signals, I would just say like practicing problems is probably the best way to go. Just because like it kind of gets you used to how to read the data path and how to like realize which components are set and which ones aren't. Yeah, that's a yeah. So the data path on the back of your worksheet, that's just something I would recommend filling in. I'm actually going to switch to the worksheet right now. How do we feel? Do we need a break or? Okay. Okay. So let's switch to the worksheet right now. I'm going to stop sharing it here. And then I need to switch what's shared here. Lovely. Okay. Okay. So if we look through our worksheet right here, so we have the pre-check questions. I will say we can skip to those a little bit later. For question 2, it's basically what happens during each of these. And I would say just like literally the slides that we just went through that describes that question. For 2.2, this is where we kind of get into a bit more practice. So I would recommend actually this should be a chart in theory because it's a little annoying to fill out. I'm just going to break this down a little bit so we have. Let's copy this over. So page, I think 2 has this question. Okay. Okay, so looking at this question, we have several different types. I'm just gonna go through one example and then we'll give you some time to work through them. Wow, my left-hand side is surprisingly even. So looking at the first one, we have our add instruction. So this is not add I, this is add, which is a what type instruction? I, so, sorry, what? Not I type, R type, yes, because this is not add I. Instructions that usually have an I at the end are I type because they're like something like or with an immediate, add with an immediate. So this is an R type instruction. So going through the list of signals, what do we have for branch equal? Star, yes, and that's because we do not care. Add doesn't ever look at the branch comparator, so we don't care what goes to that. What about branch less than? Don't care. Yes, for the same reason. What about PC cell? Select. Or +1 instruction. So +4, right, for 4 bytes. So just, this is not anyone's required, but does anyone just remember what PC cell for +4 is? Yeah, okay, we got 0. So PC select is going to be 0 for this. So what about immediate select? Exactly. So we don't have an immediate here, so we're gonna don't care for this. It can generate whatever it wants. What about branch unsigned? Don't care. Yes, anything to do with branches, we don't care. What about A select and B select for add? 0 and 0. I see a 0 and 0. Yeah, so I could say like just the zeros for most of the selectors, except for right back select, are typically like what you would think of as default. Like PC is not really default, immediate's not really default. So those are the ones for the respective muxes. Same with PC select, like +4 is the default, so it's going to be at 0. 1 is going to be the unique one, which is the ALU output. What about, huh? There's 0 because if we look at the very last one, I'm going to rotate this because yeah, so we can see this is going to be or mux A and mux B. So A is just on top, B is on bottom, and that's because they feed directly into input A and input B. So we can see that like RS1 and RS2 are both the zeros of their respective muxes, and then so PC goes with A and then immediate goes with B. And the reason for that is just because wiring wise, it looks really nice. Like in theory, you could flip them and then just rewire things, and it wouldn't affect the output. But this is just for a convention. Because it's not a branch instruction, not because it's a jump instruction. Because jump instructions don't use the branch comparators either, remember. Only B type instructions do. Jump, like JAL? JAL is actually a J type instruction, and so the only J type instruction. JAL-R is actually a weird I type instruction. Okay, and then so for ALU cell, what operation do we want? Yeah, so we want add for this. So when you're doing your data path project, this won't like just say add, it'll be some kind of signal as well, 0, 1, 2, 3, etc. But here, because we don't have that set, we're just going to write add. And then for mem read write, what do we have here? Right? Why do we have write for an add instruction? So we don't have to write, right? Because this is an add instruction. We, in theory, don't need to access memory at all, but we do just because for simplicity. So we don't want to actively access and write to memory. So here, so we want to have a 0 instead. So I think what you're thinking of was like right here, we need some kind of write back value, right?
Okay. So
yes. So you save it into the reg file, unless it's a store. Oh, stores are the only reason that you would want to write to memory. Otherwise, if you're writing something or you want to store something, it would be in the reg file right here. Okay, and then for reg write enabled, yes or no? Yes, so that would be 0 or 1. Yeah, okay, so that would be 1. And then write back select, what signal would we have here? Yeah, so ALU output is going to be 1 for write back select. Huh? The signal or the 1? Yeah, so for write back select, we have 3 valid signals that we really care about. 0 is going to be the output from memory. Have no space because it's spacing. 1 is going to be the output from ALU. And then 2 is going to be PC +4. Cool. So are there any questions with how we broke down this instruction? Okay. Why is PC's this one? Yeah, PC cell is 1, 0 here because add doesn't change how our execution flow goes. Like branch and jump instructions do, but add doesn't. And so by default, if it doesn't change our flow of execution, then our next instruction that we want to select is PC +4, which is selected by 0. Yeah, so write back select is basically, so you'll notice that right here, like it's kind of upside down. This is actually basically what it's doing. So I would go based off of this, but basically our write back selector is telling us, so this is right back selector. Also, this is just a side note. If you're in CSM, you might notice that they'll have 210, and you might notice on certain older resources there'll be 210 as well. I don't actually remember exactly which one this class teaches right now, so I'll check during our work session in a minute. But basically, like, just follow whatever data path is given to you, because like I said before, like, our selector values can change. Like, it really doesn't matter. It just matters how you're wired up. But basically what write back selector does is it's a 2-bit value, so 2-bit selector. And it tells us basically, okay, what do we want to write back eventually to the reg file? So this is to the reg file. And so based on, let's just use like values A, B, and C for now, just because it makes it easier. So we're gonna use A, B, C until I confirm which one's which. But basically, like, oh, if it's if write back selector is set to 0, then what's going to be written back to our register right here? So RD is going to be PC plus 4, and then ALU or memory. Okay, so I'm going to give you a few minutes to work on breaking down the other instructions. So I would say focus on, I would say load is interesting. Save is interesting, I think. Or let's do. So I would focus on these first. That's pretty much all of them, but yeah. Yeah, this one or the slides one? The slides one. Okay, let me reshare. Oh, I also realized, oops, I need to reshare this. Okay, real quick clarification. I can confirm from the slides at the very least that PC plus 4 is at 2, ALU is at 1, and mem is at 0. So same as what's on the slides right here. It appears that our discussion has gone out of sync, so I will bring that up. So because it has it flipped upside down. Huh? Yeah, they have it just flipped in terms of order, but the bits breakdown is still the same just because it doesn't change like where the bits are in memory.